Graphs are great. Graphs can be used to describe so many relationships between data and between different concepts even. And so let me start off talking about graphs by looking at this diagram. This is something I don't believe it's proprietary or copyrighted uh, in an article about Amazon, Amazon.com. I'm sure you're familiar with them. And these are their core concepts, but they also describe how the concepts are related. They call this a flywheel. Flywheel is what happens in an engine that kind of keeps it going when nothing much is going on. And so you have these business concepts here with lower fixed costs. That's a business concept, right? Association of low prices and selection, better value, something, I can't actually read it, bigger selection. And the central thing here, as far as this picture is concerned, is more buyers. The thing is, this is a graph. And so someone at Amazon, no, I'm sorry, I forgot the guy's name, drew this picture to describe how the Amazon principles were related to each other. But it's a graph. So a lot of times when we look at examples of graphs, there's like between sets of letters A, B, C, D, E, F, G, or pairs between cities or nerve endings or something like that. But it doesn't have to be something hard or scientific. And so much computing happens in the business world. I mean, one of Amazon's big successes is Amazon Web Services, which is a computing platform. And so this can come up in almost anything that you might be asked to do in computing or in various kinds of mathematical modeling. So graphs are great. We're going to look at some things with this graph as we go on. So what's the problem? The problem is there is a tremendous amount of vocabulary about graphs. And so you have to learn a lot of words in order to talk about graphs in a useful way. And so that's mostly what is going to happen right now, is introducing graphs and their vocabulary. So the most important thing to get out of the way is the abstract thing, and you can keep coming back to the abstract thing and seeing how various things that you might think of as a graph are related to other graphs. So the abstract thing is you have V, which is a set of vertices. So that's just a set. Large, small, we don't know, numbers, names, strings, business concepts. It's a set. And E, those are called the edges. And those are ordered pairs of vertices. So E is a subset of V cross V. This is almost useless except when it's not. So the thing is, so each element of E is an ordered pair, the initial point and the terminal point. So the picture, which is strictly speaking a metaphor, so what you have is you've got a vertex V1 and a vertex V2 and an edge, the ordered pair V1, V2. You can draw that with limited, the usual limitations about drawing stuff. I mean, page is only so big. You can put an edge in between, and there it is. So it starts at V1, goes to V2. The edge is in pink. So this is the basic idea of a graph. And so you've got a bunch of ordered pairs of things. So this is a directed graph. Some people say digraph. I don't happen to like that, but it's not wrong. So there it is. It's directed because you have an ordered pair. There's an ordering to how you consider the edges. You have the initial point and the terminal point. There's another concept which is called a multigraph. And I'm surprised there's a simple way of describing these that the book doesn't use, so pay close attention. So what you have is a set of vertices V. I'm not going to write that out because that's the same as it was. But now the edges are, or let me draw a picture. I think that'll kind of help us um, see what's going on. So a multigraph allows the possibility that there's more than one edge connecting um, two vertices. So what I've done here is I've drawn a pair of vertices and a couple of edges that that go from V1 to V2. So there's an upper one in the picture and a lower one in the picture, but they're different. And so what the book says is, yeah, you can go from Pocatello to Idaho Falls. They don't actually talk about our part of Idaho, but they say, oh, you can go between cities. I mean, but even right here, you can go from Pocatello to Blackfoot, say, on I-15, or you can go from Pocatello to Blackfoot on, I think it's US 91 that goes through Fort Hall. Two different ways of connecting Pocatello and Blackfoot. So, so there's a simple way to handle this, which is that in a multigraph, the edges have a structure to them. So in this case, I'm not sure how well the colors come through, but the upper one is pink and the bottom one is green. And so you can color the edges, and that makes them different. So what we can do is say that the edges are a subset of V cross L, and I'm going to say L is the labels. There's a little bit of problem with that if something doesn't have a label, but we can come up with a default label or something. There's a way to do it. So this language of Cartesian products saves the day, and that's the way we go. A colored graph, the vertices have labels. In a multigraph, the edges have labels. So it's all about what's labeled. And the color graph, I mean, the labels might be, Subaru, Toyota, Ford, Chevy, but they'll still call that colors. So they want to be more abstract. So this is a graph. It's not a multigraph. I don't see anything where there are two ways to get from one concept to another. So there's the deal. Okay. There's a special graph which is called a complete graph. And the book claims that there's a standard notation, K sub n. It's not standard, but that's okay. And so that says for every V and W, VW is an edge. So I'm going to write that using quantifiers because that's the most compact way to write it. So you can go from any vertex to any other vertex. And so there's the situation. Okay, so that's a complete graph. Okay, the next piece of vocabulary that we have to, oh, by the way, this is not a complete graph. I don't see a way to get from, there's no edge from more sellers to better value. So it's not complete. There's a path that goes from one to the other. And so that's our next concept. The path is you go from more sellers to better selection to better value. I guess that's prod for product or something. Anyway, so you can make a sequence of edges here to here, here to here, and that tells you a path from this vertex to this vertex. So a path is a sequence of edges that match up in the following sense, that the first one might go from A to B, and then the second one has to go from B to someplace else. That's what makes it a path. First one goes from A to B, second one has to go from B to someplace. And then once you're at some C, then the next one has to go from C. So that's just the common concept of a path. If you think about hopscotch, that gives you several paths from the beginning to the end, because you might There you go. Okay, so I guess that's, um, I don't know if people still play hopscotch. Okay. So that's the idea of a path. And so one of the things that you think about with graphs is a path. That would be more important for geographical kind of things than for concepts, but it's a thing that happens here. A graph can have a subgraph. This is a very important construction as far as studying abstract mathematics. And it has one important aspect in computing. So on the math side, you're going to do this all the time. On the computing side, you're going to do one style of this many times, but you're really only going to do one thing. So a subgraph has the vertices are of the subgraph are contained in V, so that just makes a subset. So the vertices of the subgraph are a subset of the vertices of the original graph. But then you got to worry about what to do about the edges, and so what happens is that if AB is in V, then I'm sorry, AB is in V prime, then AB is, I screwed this up so badly. Let me write this over, sorry. If I have an edge AB that is in the subgraph edges, then it must have come from the original graph edges. So finally, with all these crossouts, but I guess you can graph from my crossouts or something. So if you have something that's in the edges of the subgraph, then that must have come from the new graph. You don't introduce new edges. So that's what makes it sub. You get some of the old ones. And so there's one very important graph called a spanning subgraph. I said graph, I'm sorry. One very important subgraph called a spanning subgraph. And this has to do with efficiency, which is why spanning subgraphs are very prominent in algorithms for computing, because what you have here is that a spanning subgraph has to include all the vertices of the original graph, but hopefully subgraphs should have fewer edges. It could have the same number of edges, but if it's a strict subgraph, then fewer edges. So that's the same vertices, maybe fewer edges. And that means there's less storage, less computing, less everything, fewer resources to handle a spanning subgraph. So it's the same vertices and fewer edges. So that's a big deal in computing. There's something that you can see on this one that is a very common feature of graphs. So if we start at this more buyers vertex, we can go to more sellers. That's a path, and then we can keep going on a path. Then we can have bigger selection, and then we keep going on the path, and we get to better value product. I don't know, and then we come all the way back to more buyers. So we have a path that comes back, and the starting point is the same as the end point. So that's called a circuit. Sometimes people call it a cycle. And I think mathematicians call it a cycle, and computer scientists call it a circuit. I think that's the distinction there. And so this is a path whose beginning point and end point are the same. So let me kind of color code that circuit that I have come up with here. There are other circuits in this one as well, and so let me kind of highlight those. but not everything is a circuit. Oh, there are some bigger ones. Okay, so there's the situation on the circuits. And that's not all of them, that's some of them. There's a graph feature that is not visible on this graph, but is still very visible, and it's going to explain why we talked about something that we talked about earlier. And so the connected component what that means is two points are in the same connected component. I'm sorry, I said points, I meant vertices. Two vertices are in the same connected component if there exists a path between them. So that's a relation. That's now a relation on vertices. It's not the edge relation. It's a new relation. It's the connected relation. So let me kind of highlight that because this is a new relation. New relations are very exciting. It's kind of like having a nephew born, right? So anyway, a new relation. So what did I just say? I said that two vertices, say V and W, are related if there exists a path that starts at V and boop, 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 and ends at W. So I've just kind of cartooned the path. V goes to something, it doesn't matter right now, goes to something, goes to goes to something, goes to W. So there's a path from V to W. This is in fact an equivalence relation if you allow a VV to be a path. Some flavors of graphs don't allow that. So if you allow a path from a vertex to itself, then this is an equivalence relation. So well, there is an equivalence relation involved, but let me come to that in a second. If VV can be in E. Otherwise, you don't get the reflexive part. So the thing is, the connected components form a partition. It's like you can't get there from here. And so you get one subset, which is a connected component. And if you can't get to another subset that's a connected component, so these do form a partition, and that gives you an equivalence relation. So so that's the deal. So that may not be the same equivalence relation because if you had I guess, single point by that definition, single vertex, excuse me, can't be a connected component because unless you're allowing a path to itself. So we need to be careful. Okay, so let's get to the last bit of vocabulary that we need here, which is actually one of the most difficult problems in computing and in mathematics, which is graph isomorphism. And when you look at graphs with this many vertices, it's pretty easy to decide what isomorphism is. It's when they get to be, honest data. All the connections in your brain. Now we're talking. What's that isomorphic to? So graph isomorphism, a very technical situation. So I've got two graphs. I've got V with its edges and V prime with its edges. So these are graphs. And to be an isomorphism goes like this. It's a function from V to V prime, and that function has to be injective and surjective. So that's a one-to-one correspondence. It's another way to say that. So that's going to be the isomorphism. But that's not just enough. I mean, if you have a set with 12 elements and another set with 12 elements, there are 12 factorial different ways of having functions that go from one to the other that are one to one and on to, because those are just like permutations. And so the function isn't what makes it a graph isomorphism. It also has to do the right thing to the edges. And this is a construction that happens many, many, many times in mathematics and sometimes in computing. So you have the function, and the function has to have another property. And so I'm going to write that property this way. If I have VW is an edge in one of them, that happens if and only if f of v, f of w is an edge in the other. So this is a much more actionable way of saying, oh, same vertices, same edges. But I mean, that's what we're trying to say. Same vertices, same edges. But we're trying to say it in a way that gives us handles to prove things about graphs. So this is the graph isomorphism. Given two honest graphs, not toy graphs, to decide if they're isomorphic is a very, very, very hard problem. And so it leads to a lot of other interesting problems, mostly in the computing side. Mathematicians will just say, oh yeah, those are isomorphic. I don't have to show you exactly how. But in computing, you got to actually compute the isomorphism. And so that can be a little bit difficult. So that's the beginning of the graph vocabulary, and people use these words. These are the common words in most cases, and so anything that you have that works with graphs, even in business writing, will be described quite handily by having this graph vocabulary.